Okay. For this picture, there are two words in it. One is called IGP. One is called EGP. That is an internal gateway. External gateway. The internal gateway is used in the local area network. That is LAN. Remember the LAN of the local area network we talked about in the first class? Exterior gateway routing protocol used in wide area networks. That is WAN. Their application scenarios are different. So how to distinguish them? This LAN and WAN are too abstract. IGP is called Interior Gateway Routing Protocol. EGP is called Exterior Gateway Routing Protocol. How to distinguish between the inside and the outside? We talked about something before. AS. That is autonomous system. I said it before. Within an AS, run the same dynamic routing protocol. The strategy is relatively simple. Is a network built by a unified manager, called AS. So what we call external and internal refers to an autonomous system, external and internal. Like a door. The outside of the door and the inside of the door are called inside and outside. Inside and outside of this agreement refers to the autonomous system. Then the interior gateway protocol refers to the protocol running inside the AS is called the IGP protocol. Exterior gateway protocol refers to the protocol running between AS is called EGP protocol. Then the typical EGP protocol running between AS. The BGP protocol currently used in the WAN. You will learn in the NP course in the future. There are many interior gateway routing protocols running inside the AS. OSPF, ISIS, RIP, EIGRP, etc. If you don't know Cisco before, I can tell you about EIGRP. Early on it actually belonged to both the interior and exterior. That is, it can actually also be used between AS. But unfortunately, it launched and opened too late. Now all the ASs on the public network are running BGP. EIGRP as a whole was born late. That is, appearing late. We will learn the configuration of EIGRP later. You will find EIGRP also needs to configure the AS number. So if some students know BGP, you will feel very kind. Because only the public network, that is, the AS number is only required between ASs. So you come across a protocol. The AS autonomous system number needs to be specified. Means that it can run between autonomous systems. It is not a pure interior gateway routing protocol. For EIGRP. First, it was launched relatively late. Second, it opens relatively late. That is, it can run both in AS, can also run between AS, and want to compete with BGP. But unfortunately, when it's launched and it's open to the market as a whole, the market has long been occupied by BGP. So EIGRP is sorry. Many functions have been developed, but in the end it was not put into use. EIGRP itself has a very good protocol mechanism. Just make it easy for everyone to understand. Will be covered later in the advanced course. AS internally called IGP. Between AS is called EGP. This is the difference between their names. Including AS itself is also a concept in BGP. It's better to take it out. Some students may ask, does internal mean the kind that does not include operators? In order to facilitate your understanding, I will draw another picture. For example, this is operator A. This is carrier B. This is the company. There are many routers in the company. Of course, between operators is also a router. But I won't draw. I'll just draw it. This is the device we're talking about. Future. The company may have business interconnection with the operator. First of all, let's talk about where these things are running. The IGP protocol will run within the company. Whether it is IGP, OSPF, or EIGRP, running between these devices. If the company is relatively large, need to do some information docking with the operator. A company is an AS. Is a private AS. Also numbered. The operator is a public AS. It also has an AS number. BGP is now running between the two ASs. Although now, only BGP is used in EGP. Then between operator A and operator B. They run on the public network. It also runs the EGP protocol. So we can also know the difference between them. Of course, the IGP runs among them. Because operators are now using ISIS of IGP protocol. OSPF they are not used. This is the usage scenario of various routing protocols. I made a distinction for you. Then when you come into contact with ISIS in the future, it is necessary to learn to be biased towards the direction of the operator. You will only touch this. Cisco doesn't seem to talk about it. Sometimes I will take it out and say it simply. But don't say much about it. Because it is not part of the routing switch. In the enterprise network, you must first understand. Within an autonomous system, we all use IGP. Carrier A is also an autonomous system. Of course. Carrier A between various distributions. They are also different. The autonomous system also runs IGP. It is also EGP when docking. It's all the same. Okay. Next. What we're going to talk about is EIGRP. That is the first dynamic routing protocol we touched throughout the NA phase. Same. Let's talk about a distance vector routing protocol and a link state routing protocol. Let's first look at the content of EIGRP. I just introduced to you. It is also an IGP protocol. Interior Gateway Routing Protocol. Also used inside an AS. It was previously a Cisco proprietary protocol. But now it's publicized. Need money. So, we often still treat EIGRP as Cisco's proprietary protocol. Because very few people actually use it. Unless it's still a pure Cisco environment. Otherwise it's hard to see. And in EIGRP, it will have its own algorithm. This algorithm is called the diffusion correction algorithm. That is dual. Also known as diffuse update. Well, I just told you. Like SPF. It is the algorithm used by OSPF and ISIS. Dual is the algorithm used in EIGRP. We will also talk about the specific content of this algorithm today, including how to judge distance vector routing protocol and link state routing protocols. Depends on what it interacts with. Because EIGRP interacts with the routing table. So we call it a distance vector routing protocol. But it combines link state. Usually. It also has link state features. But it's essentially a distance vector protocol. Okay. We will learn it formally next. There is a sentence in it. I need to give you an explanation. Here you can see. It supports many network layer protocols. Apple Talk, IP, Novell, and NetWare etc. But in fact, now the most used network layer is the IP protocol. Some students will ask, can static routing be considered an IGP protocol? Okay. For static routing, it cannot be considered an agreement. A static route is just a single static route. Because it has no algorithm. It also does not need to specify a range. Static routing can also be used on the public network. Because it is not an algorithm. So it does not belong to the IGP agreement. Or the EGP agreement. Let's explain IP. The others are not commonly used now because we're not going to explain. For the IP protocol, the first thing you need to know is when we are talking about the third floor. I actually told everyone. The IP protocol we are using now is IP version 4. Internet Protocol version 4. We now also have an IPv6. You may be interested in IPv4 and IPv6. It's more about staying on the IP address. But the IP address is actually a field in the IP protocol. A source IP and destination IP is a field. Actually, what we're talking about, IPv4 and IPv6. The two large framework protocols. Then why is there only one IP written here? Is it because we still have to compare with OSPF? What OSPF learns in the NA and NP stages is version 2 of OSPF. So in fact OSPF also has version 3. So for the current IPv4 network environment, when running OSPF, in fact, version 2 is used. If the IP protocol migrates to version 6 in the future, let's run OSPF to use version 3 of OSPF. Because there are some mechanisms in version 2 and version 3 are different. And for different IP protocols, what it serves is also different. So, if the future really migrates from version 4 to version 6 era, we are now deploying IPv6 addresses on a large scale. This is the overall transition. If in the future, we hope to see single-stack IPv6 all over the world. Relatively speaking, it is still relatively long. Have to be decades. Single-stack means IPv4 is completely useless. IPv6 only. In fact, this is a very long process. But for the present process, if it really came to that age, IPv4 has really migrated to IPv6. When you go to use OSPF again, version 2 cannot be used. Can only use version 3. That is a transition issue between protocols that I highlight. Protocols like OSPF. It is impossible to make a smooth transition. You have to completely modify the current overall configuration. Because the version is different, the configuration is also different. It has no way of smooth transition. But why bring it up and talk about it? Because of EIGRP it's not the same. EIGRP is version agnostic. That is, whether it is the current version 4 or the future version 6. No matter which IP protocol you choose, EIGRP works as usual. It also does not need to modify the configuration. It is unversioned. So in the future if the transition, it can do a very smooth transition. Updates with little impact on configuration. It does not serve version 4 or version 6 alone. Here's the difference between them. Next, let's talk about its characteristics. A lot of this is nonsense. I pick some key ones. First let's talk about this advanced distance vector. It is an advanced distance vector routing protocol. Look here. It is a distance vector routing protocol. It's just more advanced. Where is the senior? I just said 4 RIP. It's like someone gave it a cooked meal. It ate directly. It looks at the devices at both ends locally. Then send the data to others. But for EIGRP, are different. For these devices, it is also the interconnection of multiple devices. This is R1. This is R2. This is R3. After R1 calculates his own, directly give to R2. Then, for R2, it will take in R1. After that, it is not calculated locally before sending, but after taking it in. Take your own and send it directly to the other party. Then calculate it yourself. Every device is like this. So, its overall sending speed is much faster than RIP. Of course, from the point of view of what we just said about eating, it doesn't really make a difference, because it also passes the routing table. But it's coming soon. It will not be counted and sent after it is received. Instead, after receiving it, I even take my own and send it out together. Then run it locally. It's an algorithm question. The specific algorithm will focus on the NP stage. Algorithm is not as simple as I say now. In the NA stage we don't need to know much. Secondly, it has a feature. Fast convergence. EIGRP has a table called the topology table. If you have learned OSPF before, you probably know that OSPF also has a topology table. But it is not as strong as EIGRP. Topology table in EIGRP. It can put some backup paths inside. Pay attention to my words. You can put some backup paths. What are these paths used for? If there is a problem with the main line in the future. For example, data to destination. I will not draw the device between the two lines. Above is the main line. Here is the backup line. Once there is a problem with the main line, the alternate line will immediately appear in the routing table. Notice, is immediately present in the routing table. Then achieve a fast convergence. Let me tell you. How is this different from the static we just talked about? Some students may have doubts. Then the static interface was broken just now. Didn't the other one appear immediately? Do you all have such questions? Just now that also appeared immediately. But it is not the same as dynamic routing protocol. The one that appears immediately is due to your manual configuration. A separate backup path is allocated there. This is a static configuration. Please pay attention. This is the configuration. And for dynamic routing protocols, the backup line is calculated by itself. I guess it's a backup line. It is calculated. It's not one of your configurations. So for EIGRP, it can now calculate the data in the network. For example, there are multiple routes to the destination. And it can choose if this line meets the principle of entering the topology table. We can put it in the ellipse topology table. If the main line fails, I can immediately make this line appear in the routing table. And forward. It's a really nice mechanism for it. OSPF can't do it. Achieve a fast convergence. How can it be achieved? What kind of lines are eligible to enter the topology table? That's a question we're going to talk about today. Including here is another one called loop-free routing. I will tell you. Whether it's what we call EIGRP. OSPF is also good. ISIS is also good. They will all calculate the topology by themselves. That is, dynamic routing protocols are essentially loop-free. Because they need to understand the information in the network. You will learn topology drawing later. When the information in the network is drawn. These network devices. How to connect each device after receiving the information. They can be calculated by themselves. After the calculation, it can know whether there is a loop in the network. And has its own some anti-ring means. Based on different mechanisms. But we won't talk so deeply at this stage. So everyone understands that it is acyclic. That is, for each dynamic routing protocol, You don't even have to worry about loops. Unless you have some redundant configuration. For example, you configure a virtual connection for OSPF. This may create a loop. But we will not at this stage. That is, if you don't configure it normally. Do not do those configurations that make it cause a loop. It won't have a loop. We won't talk about the trigger update later. Because when I talk about appearances, we'll tell you about this. Let's look down. Here is an equivalent load balancer. And non-equivalent load balancing. In fact, the balance is not appropriate. In fact, it is more accurate to say that load sharing. Because it can't achieve true balance. The traffic will still be worse. But let's just say, do equivalent load and non-equivalent load. What does it mean? This has to be a separate picture. Okay. Let's take a look. For example, now here is a device. There is also a device here. There is also a device above. There is also a device below. This is R1. There is a route on the right. It is on the 1.1 network segment. For example, after I run EIGRP. So now R1 can learn this route from both above and below. Then according to the routing table addition principle. Under the same agreement. We start by comparing the routing metrics. Whoever has the smaller value will be added to the routing table. If the measure is the same. For example, above is 1000. Below is also 1000. Of course it's usually not that small. Wait a minute, we'll look at the specific parameters. Then they will all be added to the routing table. Since they are equivalent. We call this table addition equivalent load sharing. Then there is another situation. If the measure is different, we call it non-equivalent load sharing. But you may find it a bit strange. If the measure is different, isn't it possible to add the smaller metric value to the routing table? Shouldn't the ones with larger metric values be added to the routing table? But EIGRP is different. EIGRP can use some special methods. Let both appear in the routing table at the same time. If I change it to 10,000 above, the following is still 1000. These two items can be added at the same time. But the following one is better. The above one is worse. Unequal load sharing. I can have them appear in the routing table at the same time. How to do it we will see today. Of course. Today we will show you the contents of the topology table. Let's talk about this when the time comes. Just know that it has such a mechanism. Actually not very common. Let's go on. Flexible networking design. It is to update later. It is for network equipment. No restrictions. Not like RIP. Finally. Talk about this multicast and unicast. For multicast. First of all, EIGRP uses multicast for. Our overall data interaction uses multicast. Then for RIP. RIP version 1 uses broadcasting. Bad radio. I simply draw a picture to explain. For example. Now this device. Run RIP. For RIP. When the information is updated. Suppose there is a switch in the middle. A PC is connected here. It's okay. Two routers connected to one switch. There is also a PC connected to this switch. Then if RIP is delivered through a broadcast form. When the two of them are exchanging information. PC can also receive this data. That's the bad thing about broadcasting. It is not necessary to receive this data. Secondly. Now they are exchanging routing table. It acts as a PC. What if it's an attacker? The data of the device is broadcast to the PC in this way. It's for us. The privacy and security of the network is also not guaranteed. So broadcasting updates is not a very good approach. For unicast, you can't see it in EIGRP. You have to be inside OSPF to see it. You will learn the NP stage in the future. When learning OSPF, you will learn about a network called NBMA. Under this type of network, it communicates overall via unicast. But we can't reach it at this stage. Of course, OSPF still uses multicast more. Same as EIGRP. This is the communication between them. How to understand this multicast? In fact, I told you briefly before. Multicast is. These devices can be added to the group before communication. So how do we define multicast when we run EIGRP? Is that you have EIGRP running on the device. And after the declaration is completed, the group will be added automatically. This is called protocol-based grouping. It is added automatically. What's the benefit of this grouping? Is equivalent to. You can listen to an address of this multicast once. I will send some information in the future. Send to such a logical multicast address. As long as the device is added to this group, I can monitor the contents of this address. Then I can receive the data. This is what we call multicast. You will learn about the specific content of multicast in IE. Like WeChat group chat. You want to message someone right now. You have several ways. For example, private chat one by one. You can also choose. Pull these people into a group. Then talk to all of them. Then some students may ask, what is the difference between broadcasting and it? Give another example. For example, your company has about 100 people. You have a WeChat group. Suppose there are 20 people in your department. You have a better relationship. You have a separate group chat. This is your group. For broadcasting, it means you are within the scope of your company. You send a data that everyone can hear. But sometimes, you just want these 20 people to listen. You have a small channel. This is called multicast. If you want to send data to others alone in the future, sending one by one is called unicast. Look down. Support VLSM. We still have to draw a simple picture. Don't look at it just a few words. There are a lot of things involved. A PC. 2 routers. This router has a network segment here. Suppose this network segment is 172.16.1.0. 24-bit mask. Okay. It is clear. This is a Class B address. No matter what the bar 24 behind it is. It must be subnet. Otherwise, according to the rules, it starts with 172.16. Should be a 16-bit mask. This is a standard Class B address. And it is still a more specialized address. We talked about address classification before. You will find that it is subnet. If the routing protocol does not support VLSM. For example, this network segment is finally transmitted to this device. It learned, but not supported. Don't care what the data is. In the end, it will only learn and spread according to the main class. That is, the final data goes here. For this device, it passes 172.16.0.0. 16-bit mask. Because the main class of this address is a Class B address. Then the device will eventually propagate and learn according to the Class B address. Then if the device supports VLSM, it issued 24. Then what it learns is 1.0 bar 24. So if the device does not support VLSM, what it actually learned was wrong. Because it is obviously a 1.0 bar 24. It learned a 0.0 bar 16. This is definitely not right. So this is what we call VLSM. Okay. Let's finish the last point. Finally, there is a support for WANs and LANs. This is what I just told you. When EIGRP first came out, it supports the use of the wide area network. That is, support use on the public network. Why not now? Because it appeared relatively late. When it comes out and wants to open the market for free, the entire internet is deployed. And it charges. So gradually it will be forgotten by everyone. How much have you forgotten? Many people only think that EIGRP is a Cisco proprietary protocol. Just like OSPF. Many people don't even know. It used to be deployable on the public network. Actually, this agreement is really powerful. Now only used on IGP. But in a moment we will learn about its configuration. Everyone should know. It will have some corresponding AS number configuration. When we are learning EIGRP as a whole, there are 3 tables. Look. Neighbor table, topological table, and routing table. When we learn OSPF in the next class. Also 3 tables. Neighbor table, topology table, routing table. Both of them are the same in this case. The overall timing is not quite right. So whether it is technology or market, timing and opportunity really matter. Okay. Let's take a look at these tables. For dynamic routing protocols, its appearance will be more. Because you can only see static routes in the routing table. It has nothing else. Static routing does not have a static routing table. But dynamic routing will have a lot of appearances. Because it's complicated. So many tables will be generated. Let me tell you the contents of the table first. For example, there are now 2 devices. EIGRP is running between the 2 devices. Then they will exchange messages with each other. They interact to do hello packets. Is a greeting message. Then after the exchange of this message, the 2 of them will establish a neighbor. It's like you open the door and say hello to your neighbor. You 2 will be neighbors from now on. Once the 2 devices establish a neighbor, each will generate a neighbor table. The contents of the table. It's the picture I'm showing now. Let's take a quick look. First look at the first H here. 1 is 0. 1 is 1. This is the order in which neighbors are established. In computer language, the first digit is always 0. The second digit is 1. So it means that the following is the first established neighbor. The above is the second established neighbor. This is the order between them. This is just an identification. The following is more important. This one is called address. Please be careful. Whether it is the EIGRP we are talking about today, or OSPF in the next class, this representation is called the neighbor table. There is a very important word in the neighbor list, called I see the neighbors. That is, parameters seen by the device in the neighbor table. Not its own parameters, but the parameters of the neighbors. So this address, it is not the address of the interface of this device, but the neighbor's address. Everyone can see. This device is R1. Then according to the current overall configuration specification, it should be XXX1. But what you see here is the address of point 2. That is, here the device looks at the neighbors. It looks at the address of this interface of the neighbor. This is the address inside, instead of the address of the interface of the device. Due to more appearance, people often get confused when viewing. So I emphasize here, is the neighbor's address not the device's address. Include interfaces whose interfaces are also neighbors. Neither is the device's own interface. Go down and look at this uptime first. This is how long the neighbor lasts. That is, devices and neighbors greet each other. From the beginning to the present. The time they've been together. Don't look at the following parameters. This will be discussed at the NP stage. None of these 4 parameters will be mentioned. You will learn the protocol mechanism in the future. After learning the message, learn them again. Let's finally talk about this hold called duration. EIGRP is not only about establishing neighbors, but also to protect the neighbors. Then EIGRP sends a hello packet every 5 seconds. Then, if the device does not receive the other party's hello packet within 15 seconds, on behalf of the device thinks the neighbor is down now, the device will revoke the neighbor. That is, it thinks the neighbor is gone. It is removed from the appearance. Then this hold means every time the device receives a hello packet from its neighbor, it will refresh this to 0. Then start counting up. If you haven't received it in 15 seconds, it won't want this one. As long as the device is in the process of countdown. If it is received within 15 seconds after reading, becomes 0. Refresh. Becomes 0 again. Rebrush. It's like a timer. It's just timing. Count down from 0. Stop when the timer reaches 15. That's what I mean. I give a real example. You should go out to say hello every day. Suppose you say hello to your neighbor every 5 days. Then you find you opened the door and saw him after 5 days. You greet him. He ignores you. You say hello again. He still ignores you. 10 seconds passed. Say hello again. He still ignores you. 15 seconds passed. You think this person doesn't want to talk to you. You don't want him. You think this person doesn't reply to your message. Is he gone? The 11 here is. It's been 11 seconds now. The device has not received. Sometimes when we are doing experiments, this parameter is not particularly accurate. So it's enough for everyone to understand. Look down. This is a topology table. What does topology table mean? Let me tell you first. There is a routing table in the back here. This is very familiar to everyone. There is a D here. I'll explain what this D means in a moment. Let's go back and talk about this topology table. The topology table has an all links here. I see a classmate asked, are EIGRP adjacent routers neighbors? Yes. The device will only exchange packets with its current adjacent router. Actually, the same is true for OSPF. Must be a neighbor. Otherwise, there is no way to exchange messages. We'll wait while we make the announcement. The device needs to declare the directly connected network segment between it and its neighbors. So the device and it must be connected. Otherwise, they are not in the same network segment. There is no way they can be built like this. If they cross network segments, the two of them will not declare the same network segment at all, unless they are connected like this. Let's look at this topology table. Before this, I need to open up the experimental environment we did today. Otherwise, there may not be enough time for a while. Okay. There are several parameters in the topology table. For everyone to understand, we just look at this 4.4.4.4. Because wait a minute, we do experiments and we do it. In the topology table you will find, when data goes to a destination, there will be multiple next hops. And there are 2 parameters in the next hop. You will find that these 2 parameters are not the same. But they all appear in the routing table. So we're going to talk about something today. Let's look directly at this picture. This diagram is very simple. There is a loopback port on R4. The address is 4.4.4.4. That theoretically, there are two ways for R1 to go to 4.4.4.4. That is, the upper and lower roads. But please be careful. We're talking two ways to get to this address. But not necessarily these two paths will appear in the topology table. This is different from what everyone thinks. At the beginning of our study, we may feel that. How many ways to go to the destination? Put these roads as backups in the topology table. Not like this. Appearance in the topology table is conditional. It does not mean that there are several roads that can appear in the table, but both routes generate a topology. That's right. But not necessarily into the topology table. Whether it can enter the topology table or not, we can distinguish it according to its commands. First, type show IP EIGRP topology on your command line, called all links. If you enter a command like this, if you add all links to the command, then as long as there is a line from the originating node to the final node, as long as there is a physical connection, it will appear in that table. But if you enter the command without this all links, then there are only true topological lines will appear in the topology table. This is a real topology table. This is called the physical wiring list. That is, you can see all the lines. There may be many routes to the destination, but they do not necessarily all become the contents of the topology table. For some next hops that do not meet the conditions, won't put it in. Okay. Let's look at the routing table next. Here is a command. Show IP route EIGRP. Do you know what this means? When we check the routing table every day, it is show IP route. Now there is an extra EIGRP in the back. Just look at the routes learned from EIGRP. If there is an extra OSPF behind, just view the routes learned from OSPF. EIGRP starts with D. So here we have a question. There is a problem of managing distance in the back. When I talked about managing distance before, I told you administrative distance is actually divided into internal and external. EIGRP administrative distance inside is 90. External is 170. What does this external administrative distance mean? I give a simple example. For example, here are two devices. Both devices are running EIGRP. Then the internal administrative distance is 90. Here is a network segment. There is also a network segment here. Suppose this is the 1.0 network segment. The right device learned 1.0 on the left device. In its routing table, 1.0 the administrative distance of this routing entry is 90. But if one day there is a device here, the interface of this device and the interface of the left device are up by OSPF. Both of them are running OSPF. Agreement changed. Assuming this has a network segment of 2.0. Although here is OSPF. Here is EIGRP. But I hope the device on the right can learn the 2.0 network segment in OSPF. So how to learn it? They are not running a dynamic routing protocol. I just said different routing protocols are running between devices. They cannot directly exchange information. We have a method. Redistribution. I can redistribute. Then on this device, put the content in OSPF, introduced into the root of EIGRP. This is called redistribution, also known as routing import. Then now, it will be passed to this device of EIGRP. This device will learn the 2.0 network segment in OSPF. But for this device, it is also learned through EIGRP. But it is learned via EIGRP redistributed incoming routes. Then this administrative distance is 170. Finally, here is a summary. You may not be able to learn this at the NP stage. Might learn it in IE. Don't need to understand at this stage. And this value will not appear in the routing table. It is an implicit. As for what it is for, we can't get involved now. So you just need to understand the inside and outside. We are still talking about the interior. Now there is no redistribution involved. This is what is covered in advanced courses. Let's move on. Update multicast address. That is, when we use EIGRP, the multicast address it uses is 224.0.0.10. This needs to be remembered. By the time we learn about OSPF, that's 0.5 and 0.6. It uses 2. EIGRP uses 1. 224.0.0.10. And the protocol number is 88. EIGRP is encapsulated on top of IP packets. There is a protocol field in the IP packet. If it refers to 88, indicates that the upper layer uses the EIGRP protocol. If here is 89, indicates that the upper layer uses the OSPF protocol. You just need to know this. Don't ask you to remember it. Okay. Next we will learn the algorithm of EIGRP. The algorithm of EIGRP is called dual. The first is the acyclic path. This thing you will learn in the NP stage. Because this involves how the algorithm draws the topology. We can't get in touch at this stage. Because it is more difficult. What we have to learn is the alternate path. Fast convergence. This is the core of what we are now explaining. A loop-free backup path is, if the data has 2 lines to the destination, the above route is the best. The optimal one must be added to the table. There is no doubt about this. Then the ones that are not so good will not necessarily enter the topology table. Is to be considered. Wait a minute and we'll figure out how to calculate it. If there is a line, it is selected and added to the topology table. As long as this line is cut off in the future, this line can start forwarding immediately. This is where EIGRP is very powerful. OSPF is impossible. How to meet the conditions? This has to wait till the end. Because its overall design is at the end. We just saw. There are 2 next hops in the topology table. Refers to this. The one above will be the main line. Into the routing table. Because in the routing table you can see it too. That for now. It also appears in the topology table. We can implement its addition table later. Let's talk about this later. Here's some of the algorithms we're talking about. Fast convergence is when the overall topology changes. A fast convergence can be achieved. This word is not easy to understand. Convergence is the synchronization of information as a whole. And optimize the current forwarding path. Realize normal forwarding. The forwarding speed of EIGRP is very fast. Since it has the contents of the current topology table. So it can achieve a very fast convergence mechanism. But I tell you, if now there are 2 lines, this line is the main line. In routing table, this route is a suboptimal route. But it doesn't satisfy the condition. If it is not in the backup topology table, then it has no way to forward it immediately. It also requires a protocol mechanism. Do the calculation yourself. That is, it can be added to the list is conditional. But if entered into the table, it's switching in seconds. Let's look down. This algorithm actually draws a picture. I'm in this experiment. Restore this picture. Let's just wait and do it. Okay. Next we look at some terms. I ask everyone to listen carefully. These things you have to remember. First look at the successor router. A cost is identified here. This is for the convenience of everyone to understand. Actually, strictly speaking, a metric should be marked here. Because it is not called cost in EIGRP. Called metric. But the meaning is the same. The cost value above is a total of 40. 10 plus 30 equals 40. The following cost value is 20 plus 30. A total of 50. That is to say, it must be the above route. Because its overall routing metric is smaller. This protocol mechanism is consistent with what we said before. Both lines learned via EIGRP. The overall measure of the above line is smaller. Just take the above route. That is to say. Now if going to 4.4.4.4. Logically, it should go like this. This is called the main line. This is the line going in and out now. The lines that appear in the routing table will definitely be added to the table. Because it is the best path. Then, for this optimal path, it has a thing. Successor router. Successor router means, if the current main line is the above line, then take R1 as an example. R1 goes to 4.4.4.4 and takes the above route. For this optimal route. The next hop router of this optimal main line. Successor router. R1 if going to 4.4.4.4. Give traffic to R2. It is the successor router to the route entry 4.4.4.4 on R1. Because only the optimal route is added to the table. It is the successor router of this route. Certainly. This is all for R1. It's different if you change the device. Looking further down is the feasible distance. From R1 to destination network 4.4.4.4. The optimal total metric for this route. That is 30 plus 10 equal to 40. Further down is the advertised distance. Advertisement distance has two words. One is RD. One is AD. But we basically call it AD. It's just a title. Don't need to bother with it. Still for the device R1. The advertised distance refers to the R1 going to 4.4.4.4 in the future. Its successor router. That is R2. Feasible distance to destination network. The advertising router refers to the R1 now reaches the route 4.4.4.4. Feasible distance for its successor router to reach 4.4.4.4. That is 30. That sounds a little boring. And not easy to understand. I try to keep it as simple as possible. For example, there are 3 locations. Suppose this is A. This is B. This is C. It means A to B is 10 meters. B to C is 20 meters. Then A to C is called its feasible distance. B is the successor router of A. Feasible distance from B to C is called the advertised distance of A. Okay. Further down is the feasible successor router. Let's not talk about this. Let's talk about the feasible conditions first. Because only after the feasible conditions are met, there is a successor router. So let's start with the feasible conditions. The feasible condition is, if now there is a path, it can satisfy a parameter. We call it an alternate path. The AD of the alternate path is now less than the FD of the main path. Then it can be a qualified alternate path. Let's take this picture as an example. Now the following line. Its alternate path is the following line. Because the above is the main path, AD is the advertised distance. If its next hop router is R3, this is called its advertised distance, is 30. So now the FD of the main line is 40. 30 is less than 40 now. Suppose you use it as a backup line. Then you compare. Now indeed its FD is smaller than the main line. Then this path can be an alternate path. So what we're talking about? It is a feasible condition, called FC. If this feasible condition is met now, then the following path can be a backup path. Then it can go into the topology table. Then the next hop router on this backup path. Feasible successor router. Real mainline router. Successor router. The next hop router on the backup line. Feasible successor. Then the condition for generating a feasible successor router is the line must now be available. That is, if the current route satisfies the feasible condition, it becomes a backup line. Then this router will become FS. Feasible successor. Here are some features between them. That is to say, for a line, we have to compare such values. If this value is not met, it cannot enter the topology table. I want to ask you a question now. If it's not 30 now, I changed it to 40. So now in this path, is there still a viable post router? I saw someone ask how to choose a backup link when there are 3 lines. The same. If the 3 lines, you calculate again. As long as it is now eligible, it also enters the table. That's just in the topology table. Middle line. It will also be compared with the following lines. If both of them are exactly equivalent, then they are loads. If they are not exactly equivalent, because we'll look at 2 parameters later, they are hardly completely equivalent. As long as feasible, it becomes the backup line. Feasible successor. So now if the cost here is 40, then this path will have no backup path. Then look down. This is Cisco's metric. This 5K refers to 5 values. We haven't learned some settling yet. You can think of this K as it is 5 values. Assume that respectively the bandwidth, reliability, delay, load, maximum transmission unit. Then there are 2 values in each value. 0 and 1. 1 for reference. 0 means no reference. That is 1 for sure. 0 means negative. For EIGRP, it can refer to 5 parameters. Let's learn EIGRP for beginners. Only focus on 2. 1 is bandwidth. 1 is delayed. Usually. Reliability. Loading. And MTU. We often don't think about it. For OSPF, just refer to the bandwidth. EIGRP reference 5 options. If we refer to bandwidth, then this one is 1. If the reference delay, then it is 1. Others do not refer to 0. Then this 5K value is 10100. This means we refer to bandwidth and latency without reference to the other 3 parameters. 5K is 5 reference factors. Refers to the 5 values. By default, EIGRP only refers to bandwidth and delay. Others are not referenced. The following is the calculation formula of metric. Everyone can take a look. 256 times 10 to the 7th power divided by the minimum interface bandwidth of the link. Add the sum of link delays and divide by 10. So there are actually only bandwidth and latency in it. This is a default calculation formula. Therefore, we generally do not refer to other. 5K is 5 values. It represents the reference switch. Reference is 1. No reference is 0. When you reach the NP stage, you will learn the message. That is, all packets of EIGRP. You will both get packets. Then look at the fields one by one. Then you will see the values of 0 and 1 in this 5KR. Next, look at the message. Let's not look at the fifth. In fact, the fifth is not a real message. There are 4 EIGRP packets. Hello, update, query, and reply. Hello is to establish a neighbor relationship. Hello packet. I just introduced it to you. If the two routers are now directly connected, once EIGRP is announced, the two interfaces will start sending hello packets to the outside world. They both send each other. Then one of the devices receives the other party's hello packet. The two of them will establish a neighbor relationship. They start to learn routing from each other. Certainly, you need to declare this route yourself. That is to say, for dynamic routing protocols. Generally, there is the concept of neighbors. Only after establishing neighbor relationship can we learn from each other. I just said that too. They are hello packets sent every 5 seconds. 15 seconds if not received. The neighbor will fail. The second message is update. Send routing update. It represents 2 dots. The first point is when the device establishes a neighbor relationship. For the first time, all routes will be updated to each other at one time. The first packet is also a packet passed by the router. Because the other party has nothing about me now. Then the message sent to the other party for the first time. It is the content carried by the update message. Secondly, if there is an update in the future, also known as sending routing updates, it is also an update message. Then EIGRP sends the routing table. Give an example to explain the third and fourth. Let's draw a picture. 1, 2, 3, 4. This is 4 devices. Device 4 has a network segment here. Assuming this has an exact address. 4.4.4.4. So now running EIGRP. Device 2 can learn device 4 here. Because device 4 interacts with device 3. Device 3 interacts with device 2. Device 2 has this 4.4.4.4 route. At that moment, device 2 and device 3 were disconnected. Whether it is an interface problem or line problem, they both broke. So first for device 2. The next hop that device 2 originally went to was device 3. So now device 2 will have a consideration. It will think that now because there is a break between the two of them, neighbors fail. 15 seconds passed. It found lost this neighbor. At the same time, it thinks that the relationship between this device and it is broken. And it also thinks it has a problem now. Then this route will be gone. In addition to losing this neighbor relationship, the route to 4.4.4.4 will also be lost. But for EIGRP, now device 2 will not immediately delete this 4.4.4.4 from the routing table. It will give its neighbors who are still send a request message. So now it has only one neighbor left. It will send a message to device 1. It will ask if device 1 has a method path to 4.4.4.4. Then device 1 will reply to device 2 that it does not. If it wants to go to 4.4.4.4, it has to rely on device 2. Then device 2 will send 16 times per unit time. Device 1 needs to reply to it 16 times no. After that, device 2 will delete it. But there is a situation. For example, originally, Device 1 and device 4 were directly connected. Then device 2 goes to 4.4.4.4 and goes to the right. This is its optimal path. And possibly for some reason, this route has not been added to the topology table. Then at this time when it is broken, it will query device 1. Is there a route to 4.4.4.4? Then now device 1 will reply that it knows. Device 2 will send the next hop to the route 4. 4.4.4. Pointing to device 1. Then complete the data forwarding. This is called sending a request to a neighbor. Inquire. And the response. This is the interaction between them. Finally, there is an ACK. It is not a message. It is a confirmation mechanism. Then in the 4 messages mentioned above, there will be an ACK field. Can be filled with it. That is, all messages of EIGRP provide confirmation mechanism. After the device sends data to the other party, the other party can carry the confirmation. In the message sent to the device, represents that the message between them has been transmitted to. It is equivalent to a confirmation mechanism. When you analyze the message later, you will say, now just to briefly mention to you. Okay. We are about to enter the configuration phase. First turn on these 4 devices. Save some time. Let's go back to what we just said. EIGRP now wants to establish neighbors. Then establishing a neighbor is conditional. There are 3 conditions. The first one is that the AS number must be consistent. Because now we use EIGRP as an IGP protocol. So it does not involve the establishment of relationships between AS. So now the AS number must be the same. Secondly, 5K must be consistent. It doesn't mean the bandwidth and latency of the 2 interfaces must be the same. That's not what it means. Not the specific value inside. But 5K, this 10100 must be consistent. 2 devices establish a neighbor. The parameters they refer to must be consistent. One of the device reference bandwidth and latency. The other can only refer to bandwidth and delay. Finally, the authentication must be consistent. Certification means the messages exchanged in the device provide authentication. It is equivalent to choosing an authentication method now. It is a means of encryption. The devices at both ends are up with the same authentication method. And both parties have a password. When exchanging messages between them, it can carry the authentication method and password for transmission. The authentication parameters in both of them must be the same to build a relationship. So why do it? For example, I have a hack. I can simulate a hello message. Then I sent you a message. I can pretend to build a neighborhood with you. You can tell me your information. Then I can know the overall information of your network now. At least it is possible to calculate the network topology. There is no problem. Now I will establish a neighbor relationship with you. We start to calculate. Because in the future we learn the overall network topology. We are going to calculate the route ourselves. Then the overall topology. I can learn. So you will find. I can break into you. This is very common. But if you want to build a neighborhood with me now, then in the message you sent, must be consistent with my authentication. I use some kind of encryption algorithm. Verification method. You must also use this method. And with the same password. Otherwise, our relationship cannot be established. It will cause the 2 of us to be unable to send messages. But by default, we do not certify. Okay. Then we're done with the theory part. We're starting to get into the experimental part. Let's take a look at the overall configuration. We have joined two serial lines here. Everyone can see. Below is the serial port. First of all, for R1, we first need to give the device a name. R1. After naming, we're going to start with the configuration part of the IP address. Let's do a configuration now. 12.1.1.1. Then enter the S10 interface. Enter the interface. We also go to address configuration. 13.1.1.1. Let's configure it. This is our 2.0.0 interface. Now you should have no problem with address configuration. This address is 24.1.1.2. I now ask you a question. Think about it. Above this is an Ethernet link. Because we are using the Ethernet port, the serial port is used below. Then I ask you a question now. For example, after a while, all the addresses are configured. I ping R1 and R4 respectively from R2. I also ping R1 and R4 here in R3. May I ask when R2 and R3 ping the two devices for the first time? Will packets be dropped? If you have an answer, you can write it on the barrage. During my configuration, you can think about this simple question. S10. The address is 13.1.1.3. (34.1.1.3). Then R4. S11. 34.1.1.4. The last one. Up a loopback port on the device R4. Configure it with an address. 4.4.4.4. Mask is 32 bits. We are done configuring. Then do a test. We choose R2 and R3 for testing. Then the thought question just now. I believe you already have the answer. Then let's talk. R2 goes to ping first. Ping 12.1.1.1. See if I can get through. Okay. Pass. Dropped packets. Let's ping again. Ping 24.1.1.4. Okay. It also drops a packet. Prove that R2 and R1 R4 are connected. Let's ping on R3 again. Ping 13.1.1.1. It will not drop packets. 5 all passes. Ping 34.1.1.4. It's also all pass. When we talked about the second floor, actually told you, interfaces actually have types. According to the protocol stack, there is an interface called Ethernet port. What you see now on the LAN. All networking projects. The E port you see is called the Ethernet port. 10M. F port is fast Ethernet. 100M. G port is gigabit Ethernet. 1000M. That is 1G interface, including XG port, 10G. These are Ethernet ports. Running the Ethernet standard. The Ethernet standard is, by default, the switch can be connected in the middle. Then based on this standard, means now inside a network, there may be multiple devices. We need to be on a link, uniquely targeted to a device. For example, I want to communicate with you. Then we must request the other party's MAC. That is, we need an ARP. Let's broadcast first. See where this address is. I can communicate with you only after. This is called the communication standard in Ethernet. You need to make an ARP request. Then when you send the message, packets will definitely be dropped. Then when you sent the message for the first time, you must have timed out the request. Because you are now doing an ARP reply. There's no way you can come back in time. So it times out. So why isn't the packet dropped below? The following is the S port. It is a serial port. Serial port is a technology used in wide area network. That is, interface type under WAN. We don't use. Then its typical characteristics are peer-to-peer. Means there is no switch in the middle. There can be no other equipment connected in the middle. I don't need to request your MAC. I don't need to do ARP. I will not send ARP packets. Packets will not be dropped. Because I sent it to you. I will reply immediately. Will not request timeout. Next we are going to start configuring EIGRP. Very simple. Let's first look at R1. If we want to configure, definitely need to enter configuration mode. After entering configuration mode, we're typing router EIGRP here. Then enter a question mark. Here you can see an as autonomous system. This is called as number. That is, in EIGRP. Here is also to specify the AS number. But here it is written EIGRP 100. All four devices are consistent. We put 100 here. This is equivalent to, you give the autonomous system of EIGRP a name. But if we now configure, must be within an autonomous system. We now configure it with 100. Specify an AS number. The following word. EIGRP not only supports AS number, it also supports naming. This thing will be more complicated. When you arrive at IE, you will speak. Then when we enter the routing view of EIGRP, must first enter a command. Please pay attention. We must first turn off auto summarization. No auto summary. This command is very important. If you don't enter this command, then this will be enabled by default. There are many commands enabled by default in Cisco. You must remember each. No auto summary is to turn off automatic summary. This automatic summary is what I just told you. 172.16.1.0 bar 24. This is a class B address. If you don't turn off automatic summarization, it will spread to you. 172.16.0.0 bar 16. For example, I am on the device R1. A network segment of 172.16.1.0 bar 24 is connected. If this network segment is declared in this EIGRP, but the automatic summary is not turned off. Here at R4, what it learns is 172.16.0.0 bar 16. I learned it wrong. So this command must be entered. After turning off automatic summarization. It's a normal announcement. For EIGRP, it declares in 2 steps. The first step is to establish a neighbor relationship. That is, R1 and R2 are directly connected. They both run EIGRP. Declare the directly connected network segment. R1 declared. R2 also declares. Since the interface of R1 and the interface of R2 are in this segment, so just declare this network segment. This interface will be declared in. EIGRP starts to send hello packets out. The left interface of R2 is the same. So if we are using EIGRP to declare, first declare your direct connection. As long as the device wants to establish a neighbor relationship with the peer, the two ends must declare direct connection to each other. This is the first step. The second step is to pass the route. The reason for establishing a neighbor relationship between devices. It is because there is a network segment that wants to be passed to the other party. I will give you a simple explanation. If we don't use dynamic routing, we use static routing. You need to manually enter. Now, as long as the dynamic routing protocol is running, we only need to establish a neighbor relationship with each other. I declare a 1.0 network segment on R1. All devices can learn. This is the difference between dynamic and static. If this 1.0 network segment is gone, R1 will send link status updates to other devices. All devices will delete this network segment. This is the purpose of the declaration. Then we start declaring. The declaration is called network. We enter a 12.1.1.0 here. Then here. Let's make a positive announcement first. For example, 255.255.255.0. After the announcement, let's check. Do show run. Check router EIGRP. Is this command? Look. See what I have configured for my EIGRP. I am on this device. First up an EIGRP 100. And I declared a network segment of 12.1.1.0. Everyone can see. Right 0.0.255 behind. But the network I just entered, it seems to be 12.1.1.0. 255.255.255.0. Why did it become like this? Isn't this a bit strange? Well, first of all, you need to know. This thing is called a mask. This thing is called a wildcard. Wildcard mask. The mask we're talking about is the subnet mask. Mask is the kind of continuous 1 and 0. And 1 in the front and 0 in the back. 1 means an exact match. Is the network bit. 0 means no matching. Stands for random. Is the host bit. So before talking about wildcards, let's look here first. 3255 and 10 represent 24180. 30 and 1255 represent 24 and 81. Actually, you can temporarily understand it as an anti-mask. In the NA stage, just understand it as an anti-mask. Anti-mask is consecutive 0 and 1. And 0 is in the front and 1 is in the back. 0 and 1 cannot be interspersed. 0 means an exact match. 1 means no match. That is random. This is called anti-masking. It's the exact opposite of what we call a mask. So what are wildcards? The NP stage of this thing will focus on it. Wildcards can be shuffled. It is a mask that can jump. Wildcard mask can be a combination of scrambled zeros and 1s. Then 0 means an exact match. 1 represents random. Here is actually a wildcard. But at this stage, you can understand it as an anti-mask. Here are some differences between them. So for us, actually, we need to declare its mask via wildcard. But if you declare a positive mask, it will automatically give you the input in the form of wildcards. You will do data capture in the future. When including some strategies, use it often. ACLs including the NA phase also use wildcards, but also consecutive zeros and 1s. For R1, I just made an announcement. Then I will redeclare here. For example, network 12.1.1.0, 0.0.0.255. Let's change it. It doesn't matter whether you change it or not. But it's better to change it. We want a correct declaration. Then we also declare. Establish a neighbor relationship with R3. Then declare 13.1.1.0, 0.0.0.255. So for now, we're actually done. R1 is now declared. Direct connection with R2 and the internet segment of R3 have been declared. Then it is time to declare the network segment behind. But R1 has no network segment, because there is only one network segment behind R4. So R1 is actually done. Then take a look here at R2. We also make a configuration here. For R2, we're also going to start announcing. Then, before announcing, we must first router EIGRP 100. Afterwards you must turn off its automatic summarization. Next we declare. I'm here to show you a declaration. Network 12.1.1.0, 0.0.0.255. This is to establish a neighbor relationship with R1. So when I press enter now, everyone can observe the phenomenon. It plays the log here. Now R2 has a new neighbor. 12.1.1.1. Its interface is E00. Is up. Then it is 12.1.1.1. Since we were just now on this device. Declare interconnected 12 network segments. R2 now also declares. So when R2 declares, it sends packets out. So at the same time, R1 can also receive the data packets sent by it. Then R1 will know. Now there is a neighbor. 12.1.1.1. This is its interface. Then when they become neighbors, we'll find out. There will be a bond between them. Then they can exchange information with each other. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.